Already we discussed about the voltage to current converter. When we are giving the input voltage, accordingly with respect to the changes in the input voltage, the output current will be modified. If the input current is increasing, the output voltage should increase. Then we have to go for the current to voltage converter. Previously we discussed when the input voltage is varying, when the input voltage is increasing, accordingly the output current is increasing. If the input voltage is decreasing, accordingly the output current is decreasing. So in the voltage to current converter, the output current is directly proportional to the input voltage in the voltage to current converter. But now here we want to do the operation in reverse. Whenever there is a change in the input current, we want to change the output voltage. Means the output voltage is depending upon the input current. So the output voltage should be directly proportional to the input current. That type of circuit is called as current to voltage converter. Where we use these circuits? In general, when we observe some short circuits, in the short circuits the potential difference will be zero. We can only calculate the current. So the short circuit current can be measured. So the short circuit current we will give as an input to this circuit. It will give the required output voltage. So based on that we can guess what is the short circuit current. If the output voltage is increasing, we can easily guess, okay, the short circuited current is more. If the output voltage is decreasing, we can guess the short circuited current is less. And also sometimes when we take the solar cells, photovoltaic cells or photodiodes, in these components the current will be very much small. So our meters might not be able to detect that much small current. Even they detect also, the current will be fluctuating sometimes. So we might not able to get the perfect current because all these devices current is depending upon the light. So based on the light, these devices current is changing continuously. Now we want a faithful calculation in order to know what is the current in the solar cell or photodiode or any photovoltaic cell. So at that time, we take this current input in that particular solar cell or photovoltaic cell. So we give that current input to this circuit, that is current to voltage converter. Accordingly, we observe the output voltage. So if the current is increasing more, output voltage will also be incremented by that much amount of quantity, such that we can measure what is the current in the solar panel or solar cell. Even though we are not directly measuring the current in the solar cell, this indirect measurement will be useful to us because we are capable of measuring that voltage. That will give a very good voltage to measure. But that current will not be measurable either in short circuit condition or in the photovoltaic cell or photodiode or any photovoltaic cell. Here, by using the Kirchhoff's current law, the current entering at this node D is equal to current leaving at the node D. So the current entering at the node D is short circuit current. We have taken a current source. We are assuming the short circuit current we are representing like a current source because we are saying it is current to voltage converter. So this current IS must be equal to IF because there is no current entering into the op amp because of its high input impedance. The current entering at node D is completely going towards the feedback resistor RF. Now the current entering at node D IS is equal to the current leaving at the node D IF without any current going towards the op amp inverting terminal. We know the current IF in the feedback resistor can be calculated as Vd minus V0 by RF. By the concept of the virtual ground, whatever the voltage that appears across the non-inverting terminal of the op amp, the same voltage will appear at the inverting terminal of the op amp. So here we have grounded, so the voltage is 0. That's why VD, the node voltage at D, is also 0. Now this equation will change to 0 minus V0 by RF. So finally, because we require the output as a voltage, because it is current to voltage converter, so the output as voltage, so V0 is equal to minus RF into IS. This is indicating that the change in the input current is affecting the output voltage. So the input current is directly proportional to the output voltage. So by the change in the input current, the output voltage will be changed accordingly. So this is how we calculate the output voltage. Sometimes when we give the high frequency signals, here I have considered only DC current. But if I take the AC current and the frequency of the current is very high, in that case, because we are using the high frequency current, for the high frequencies, there might be possibility of the stray inductance and stray capacitance effects here at the high frequencies. So generally the noise will be observed. Because of this noise, oscillations will be observed in the output. We are not expecting the output to change on its own because of the noise. We are expecting the output should be changed according to the input current. But now when we are giving the high frequency signal, the output voltage is not only changing with respect to the input current, but it is also changing with respect to the noise. To eliminate this effect, we will feed back the capacitor. We connect the shunt capacitor across the resistor such that the high frequency signal will not go through the resistor. When it will be problem? If the high frequency signal goes through the resistor only, the problem will come. Because it is an inverting mode, we are connected this one in inverting mode. The output to input voltage. So the output voltage V0 is equal to minus RF by R1 into Vin. This depends on the signal that is going through the RF. If we use the capacitor, for the DC signal, capacitor blocks. But when we send the high frequency signal will not go through the resistor, but it will go through the capacitor. Because for that high frequency signal, capacitor acts like a short circuit. So by simply shunting this capacitor across the resistor, we can avoid the noise effect at the high frequencies. We can avoid the output voltage is being changed with respect to the noise at the high frequencies. This is how current to voltage converter works. Because we are taking the output as a voltage and we are giving the input as a current. That does not mean in the input we will not have the voltage. Only conceptually when we think, technically we have to speak, the output voltage is changing with respect to the input current. So output voltage and input current. This is called as a trans resistance amplifier sometimes when we want to use this for a particular electronic application. So we have discussed only one important point. With respect to the input current, the output voltage should change. For that we have designed this circuit. And where we are using this circuit also we discussed. Whenever we want to measure any short circuit current or the current in the solar cell or photovoltaic cell, this circuit is very much useful to us. We discussed about the application of the current to voltage converters in the photodiode or photovoltaic cell. Especially they are useful in converting the small current which is not measurable by us by using our meters, but they convert into voltage which can be measurable by us. It is a very important application. And in some more applications also we use the current to voltage converter in the digital to analog converters. When we are converting a digital signal to the analog signal, in that process this current to voltage converter is very much useful to us to give the final voltage signal to us. And in accelerometers, whenever you take your mobile, when you are rotating your mobile, the screen will automatically move if you do not apply any options. So how your mobile is sensing that you are rotating your mobile, because in background there is a accelerometer. This accelerometer senses the rotation and accordingly it will rotate your screen. In that type of applications, we use this current to voltage converter. The small sensing, the small rotation will be converted equivalent current, but that current is very much small. In order to measure that, we have to convert that current signal to voltage signal. In accelerometer we use. And in capacitive sensor, have you ever wondered how your bike or any vehicle, when the fuel you are filling, how you come to know whether the fuel, how the meter is working? Because when we are using the capacitive sensor, in the capacitive sensor, if this is a capacitive sensor, these two are metallic plates and this is a dielectric material. If we are filling the fuel, when the fuel level is increasing, then the dielectric medium is changing. When the dielectric medium is changing, accordingly the capacitance will change. Epsilon A by D. We are not changing the area and we are not changing the distance between the plates, but we are changing the permittivity of the medium. Because of that, C is changing. That's when you come to know the fuel is filling. Accordingly, your needle will deflect. So, in that type of the capacitive sensors, to measure any liquid level or to measure any solid level, in those types of the capacitive sensors also, because those capacitive sensors will give the output a very small amount of the current. That is not measurable by our devices because that is very much small. So we have to convert this. Converting does not mean we are changing this current to voltage. That you have to remember. We already discussed in voltage to current converter also. Whenever we are mentioning the converter means, we always mean to say that we are representing the equivalent voltage which is measurable by us. So when the current is changing, which is very much small, the voltage change we observe, which can be measurable, but the current change cannot be measurable by us. That's why only we are trying to get the output voltage. Based on this output voltage, we measure the liquid level or solid level by using the capacitive sensor. In these applications, we can use the current to voltage converter.